Now we come to chapter 18. In chapter 18, we will cover topics such as wave interference. So I'll start out with the theory of wave interference. Then we're going to talk about standing waves. We're going to talk about destructive, constructive interference. And then we'll talk about beat frequency. And then we'll talk about standing waves in strings and air columns, pipes. And then we'll treat pipes with both closed ends and both open ends, and then pipes with one open end and one closed end. So there's quite a bit of topics in chapter 18, but they are all related to the topic of wave interference, how wave interferes with each other to create standing waves, or to create a beat frequency, or to create constructive, destructive interference. So let's start out by treating the theory of two general waves that are interfering with each other. Let's say they are traveling in the same direction. So let's say you have a sound source like this. In this chapter, we're going to assume that the two sound sources are coherent. Coherent means that they are always in phase at the beginning and they have the same frequency. So there's a certain source driving both speakers, and it's constantly ensuring that they are both in phase initially when the waves first come out of the sound source, right? They're both in phase, and they're both in phase continuously, and they're both the same frequency. So then this one will travel to a certain point, let's say in space, like this, and then the equation of that would say y1 is equal to a sine of kx minus omega t. One represents the equation of the wave governing the wave coming out of the top speaker. Let's call this speaker 1, and then this speaker let's call 2, right? And then y2 will represent the equation of the wave coming from the bottom speaker, right? So y2 is a sine of kx minus omega t plus phi. So notice that I made their k the same. That means they have the same wavelength. Or their omega is the same, that means they have the same frequency, and their amplitude is the same. So it's a very idealized situation. Their amplitude is the same. The only difference between them is their phase angle. Why? Well, if they start out in phase, right, if they travel to a certain point, and that point is not equidistant between the two speakers, if it's not equidistant, then when they get here, they will not necessarily be in phase, right? Definitely they won't be in phase. They will be out of phase. So one of the waves will be out of phase from the other one by a phase angle of phi. So how will these two waves interfere with each other? How will they add up? So then we want to know y total. We're going to use a property of the sine functions. We're going to say sine of A plus sine of B is equal to 2 cosine of A minus B over 2 sine of A plus B over 2. So this is a trig identity. So since they have the same amplitude, I can factor out the A. Okay, and now let's simplify this and see what we get. So we have here y total x of t 2a, then what's going to happen here? The kx is going to cancel the kx, negative omega t, and then it's going to be negative omega t plus omega t, so then that's going to cancel. And then the negative is going to distribute in there, is going to be negative cosine of negative phi over 2, and then sine of 2kx, negative omega t, negative 2 omega t, right, plus phi over 2. Right? And then we can simplify this. Well, cosine is an even function. Cosine of negative x is equal to cosine of x. So the negative here doesn't matter. So we can get rid of this. Y total x of t is 2a cosine of phi over 2. And the 2 can divide into here, and we get sine of kx minus omega t plus phi over 2. So from this, we can conclude several interesting things. Right, so when two waves of the same frequency and a wavelength combine that are off by a phase angle and they have the same amplitude, what can we conclude? This one here is the new amplitude of the wave, right? So the new amplitude is going to be 2a cosine of phi over 2, right? And the other thing we can conclude from this is that the new wave that you get is itself is also a traveling wave, which is sine kx minus omega t plus pi over 2. This will not be true if the waves were coming opposite to each other. Then we're going to create something known as a standing wave. But this one is itself also a traveling wave, but the traveling wave is phase angle is pi over 2. It's off from the other two waves, right? So let's test to see if this makes sense. If the phase angle was 0 rads, both waves reached there and they were both in phase, right? What would happen? Then the y total, x of t, would be 2a, cosine of 0 would just be 1, right? Then you have sine of kx minus omega t. So essentially, that would be the total y. They reach there, they basically constructively interfere, their amplitudes multiply, they add up with each other, and you have 2a. They have double the amplitude, right? Now, if the phase angle is pi rads, what's going to happen? Y total x of t is going to be what? 2a cosine of pi over 2 sine of kx minus omega t plus pi over 2, right? Well, cosine of pi over 2, that's 90 degrees, right? That is 0. So that means, boom, they completely cancel each other. So being pi rads off from each other causes destructive interference. Being 0 rads causes constructive. Constructive interference, and then this is destructive. Right? How about somewhere in between? How about if they are off pi over 2 rads from each other? That means one of them is a sine function, the other one is a cosine function, right? Because sine and cosine are different by pi over 2 radians, right? Then how would they combine? Then the y total will be 2a, and then you have cosine of, so this is pi over 2 divided by 2, right? So that's basically how a cosine function will combine with a sine function when you add them. They'll give you a new amplitude, 2a cosine pi over 4. Phases are off by pi over 2 degrees. Essentially that means one of them is a sine function, the other one is a cosine function. When they add up, they give you a new wave that is amplitude 2a over root 2, right? Which is the same thing as saying root 2a, and then sine of this whole thing, and then the new wave that is created has a phase angle that is in between the two. One of them was 0, the other one had a phase angle of pi over 2, but this one has a phase angle of pi over 4, right? So now let's go back and concentrate on the constructive interference and the destructive interference. Let's try to generalize what phase angle is needed for there to be constructive interference. What other phase angle will there be for which there will be constructive interference? Well, if we go with this argument, 0 rads gave us constructive, pi destructive, pi over 2 somewhere in the middle. So the next constructive should be 2 pi radians, right? So let's try that. Radians, right? And then we have here y total. Well, this one, we're just going to have 2a cosine of pi. So we're just going to have cosine of pi is -1. So we're going to have -2a sine of kx minus omega t plus, and then this is going to be pi. Well, what is sine of kx minus omega t plus phi? We could use the law of sines. I can split this, let this be the a, and then let this be the b, right? Then we can see how this develops, right? Well, what happens? Sine of pi is 0, so that one drops. And then cosine of pi is equal to -1. Well, that -1 cancels this -1, so you essentially still get the same constructive interference. So this one cancels this one. Y total is equal to 2a sine of kx minus omega t. So essentially it's like being 0 radians, right? So we can now generalize this. We can say any radian difference, 0 or 2 pi or 4 pi or 6 pi, will cause complete constructive interference, right? So 0 means there is no phase difference between the two waves. 1 means 2 pi radians, 2 means 4 pi radians, 3 means 6 pi radians, and so on and so forth, right? So now what's going to happen if what's the next one that's going to cause destructive interference? We saw pi radians gave us destructive interference, right? How about 3 pi radians? Sine 3 pi over 2 is 0. Immediately we know that that's 0. That one disappears. So therefore the rule for destructive interference is if the waves reach a certain point in space and they are off by either pi radian, 3 pi radian, 5 pi radian, 7 pi radian, right? So then we can generalize this. We can say, what's the general rule for the n now? Well, we can't have n is 0 because 0 would mean 0 radians, right? So it has to be n is 1. Can we have n is 2? Well, if we had n is 2, it would be 2 pi radians. It will give us constructive, right? So it has to be n is 3, n is 5, n is 7, n is 9, so on and so forth, right? It has to be odd integer multiples of pi radians to cause destructive interference. Destructive. Constructive. Okay? Now let's generalize this to a certain point in space, right? So let's call this distance R1, let's call this distance R2. R1 minus R2, I'm going to call delta R. So that's the difference in the distances, right? The argument that I'm going to make is if I divide the distance in the distances by the wavelength of the wave, right? So what am I going to get? Well, I'm just going to get basically meters over meters, and it's a unitless quantity, right? If that's equal to phi over 2 pi, right, then that causes constructive interference. Well, if the phase angle is 0, right, it's constructive interference, that means delta R is 0. So when would delta R be 0? If the spacing was exactly equivalent. So if you were sitting right in the middle of the two waves, right, and then this is R1, R2, right, and then if you're right in the middle, R1 would equal R2, delta R would be 0, and then the phase angle will be 0, right? Now, if you sit a little bit on the side, let's say here, then what's going to happen? This distance R2 is going to be shorter, and then the distance R1 is going to be longer, right? If the difference of the distances divided by the wavelength is phi over 2 pi, so when is the next phase angle that will cause constructive interference, right? So phi is equal to 2 pi radians, right? 2 pi radians. Right, so if you put 2 pi here, what are you going to get? dr over lambda, you're going to get 1, right? In other words, dr is equal to lambda. So in other words, if this is bigger than this by an amount equal to the wavelength, then the peak of one wave will still meet the peak of the other wave, right? And they will constructively interfere. And is the next one where they will constructively interfere. Then you have to move over a little bit to the side again, right? And then this distance will be longer, R1, and then this distance will be shorter, R2, right? So then when is the next one? We put phi is 4 pi radians, right? So dr over lambda is going to be 4 pi over 2, and that's going to be 2. So as long as the difference in the distance that they travel is equal to twice their wavelength, right? Then that causes constructive interference again. The peak of one wave meets the peak of the other wave, right? So what's the generalization then from this? We could put 2 pi n over 2 pi, and then this one cancels this one, you get n lambda. So dr is equal to n lambda. This is usually the way that you will see it expressed. Now, what's going to be the rule for the destructive interference? Now I can use this general relationship, right, and apply it to destructive interference. So dr over lambda is equal to phi over 2 pi, right? And then I'm going to put phi is equal to pi n. dr over lambda is equal to pi n over 2 pi. And then, well, we said right in the center is when you have constructive interference, so that is n is 0, right? And then somewhere off to the side, we said, so this is also constructive interference, and between n is 0 and n is 1, you're gonna get what? You're gonna get n is 1 of the destructive interference, right? Why? Because at this location, right, you're gonna have R2, you're gonna have R1. The difference in their distance is going to be equal to half of the wavelength. So they're closer together. The peak of one wave meets the valley of the other. They destructively interfere. So the other way to say it is that they are pi radians out of phase with each other. So pi radians out of phase occurs earlier than 2 pi radians out of phase. So if you're sitting here, you hear a constructive interference, you hear a loud noise, music, right? Then you walk a little bit over, you hear destructive interference. And if they're completely coherent, you will not hear any music at all. You will completely cancel each other out. And then the next one is going to happen right here. Then the delta R is going to be 3 lambda over 2. That means that 1.5 wavelengths. So this one, they're half a wavelength difference. This one is a 1 wavelength difference. This is 1.5 wavelength difference. Then 2 wavelengths difference, and so on and so forth. The other way that we can write this, so that it won't be n is 1, n is 3, n is 5, n is 7. If we want it to be kind of similar to how this one was, 0, 1, 2, 3, 4. So we can write the rule for destructive interference a little bit different. We can say n plus a half times lambda, where n is equal to 0, 1, 2, 3, 4, 5. A lot of textbooks do it that way. So the reason why is because it works out to be the same as here. If you put n is 0, you get half a lambda. So then that makes it easy, right? Instead of saying you have to start with n is 1. If you put n is 1, you get 1.5 lambda, which is like putting 3 over here, right? 3 over 2 is 1.5. If you put n is 2, you get 2.5. It's like putting 5 over there. And then if you put n is 3, you get 3.5. It's like putting 7 over there, right? So if you want, then adopt this notation, right? Then it basically works the same as here. You have n is 0, 1, 2, 3, 4. This is n lambda. This is n is 0, 1, 2, 3, 4. N plus a half lambda. So then this one will be n is 1 destructive. Then we can say this is n is 0 destructive, right? You start with n is 0. Then you have n is 1 constructive. Then you have n is 1 destructive. So with this way of doing it, you don't have to skip 1, 3, 5, 7 like this. You'll just go 0, 0, then 1, 1, then the 2, 2, and so on and so forth, right? Like that, right? This will be also true when we are talking about light waves in optics. 2 light sources come and go through 2 slits. They are originally coherent, and then they make an interference pattern on the wall, right? So when we get to that topic, you'll see that it's pretty much the same. We have covered this and we understand this. We will give some examples of how to use this in some problems, okay? Thank you very much.